So Charles Dancak is a trainer and consultant. He's based in the Silicon Valley with Betasoft Consulting, who is a distributor for scientific analog. And he regularly teaches online SystemVerilog training courses with UC San Diego. In 2007, he introduced the first SystemVerilog workshop at the University of California Extension System. He spent 10 years at Synopsys in HDL-based design, simulation, and DFT. And he has developed hands-on courses in HDL design and verification, nanometer, ASIC flow, and DFT. He's taught them in Europe and Asia. He began his career as a technology engineer in one of Intel's wafer fabs, and his interests include the FinFET transistor and its device physics. He has a master's degree and a MSCE and an MS in solid state physics. So thank you for attending, and thank you for presenting. So yeah, we can play the video. Go ahead, please, Tasmia.
Good morning. Welcome to our mixed signal session. My name is Charles Dancak, and I'll be talking about a UVM test bench for an analog mixed signal circuit block, an audio bandpass filter with various programmable modes. I'm based in Silicon Valley. I've worked at companies ranging from Intel to Synopsys. I currently consult with Betasoft. I've also taught SystemVerilog for a number of years at the University of California Extension. Let's dive into it. We're going to be looking at a UVM compliant test bench written from scratch to verify the features of an automotive style bandpass filter. Our objective is simple. We want to bring in all the familiar UVM enhancements into the AMS domain. Modular components, TLM connections between components, UVM sequencing and phasing, and configurable test length and other knobs. We'll rely on XModel from Scientific Analog. XModel is a plug-in extension to logic simulators like VCS. It'll handle the analog content. We'll look at the UVM component hierarchy. We'll drop down and investigate the fixture submodule that contains the DUT itself, as well as XModel instrumentation to apply analog inputs and measure analog outputs. Here's our UVM component hierarchy sitting atop the fixture submodule. It's a typical UVM environment. We've got 3 consecutive sequences being generated. The data packets are sent into the driver, which then transmits the fields over this interface bus to the DUT inputs. On the output side, we measure peak-to-peak amplitude going into and out of the DUT and send those real values over this interface bus to the monitor, which reassembles the data into packets. And over standard TLM pathways, we send these packets on up to the scoreboard, whose job is to compare the actual transfer gain, measured down here, versus the expected transfer gain looked up from a SPICE reference model. This is a set of 8 lookup tables generated from SPICE. Since we're applying purely random inputs to the DUT, there's no guarantee that we've covered all the operating scenarios. So we've got a coverage object to gather metrics, and we'll see if we can hit 100%. Here's our filter. It's an active filter with this 2-stage op-amp at its heart. It's got an RC feedback network with the CMOS transmission gates switching different R and C values in and out under the control of this digital logic. There are 4 control bits. The 3 least significant bits choose the mode, such as M7, and the most significant bit, when asserted, puts the entire design into power down bypass. The op-amp is then cut off from the supply and from the bias voltage, and there's also a bypass path directly from in to out. This add-on toolbar shows that XModel has been installed, and let's try pressing this push button, which invokes ModelZen. ModelZen extracts SPICE accurate device models coded in SystemVerilog for the whole filter. To see how it works, let's focus on just one transistor M0. In its SystemVerilog description, only the width and length were specified by the designer. Everything else, the threshold voltage, parasitic capacitances, etc., were curve fitted by Model's End silently running SPICE or Spectre. And what we get is a ready to simulate sign-off quality SystemVerilog model of the entire filter. Here's our fixture submodule containing the DUT, and let's look inside and see the X model instrumentation used to apply inputs. We've got a chain of several X model primitives, starting with the random frequency chosen by the UVM sequence, 12,000 Hertz in this example. We first convert it from real type to X real, which is one of the workhorse types in X model. And to convert a constant into a waveform, we integrate over time and get a ramp. If we do that modulo 1, it drops back to 0, starts all over again. So we get a sawtooth waveform. We can scale that by 2 pi, feed it into this sine function, and we get a 12 kilohertz sinusoid. The top level packet clock controls timing. And so we'll apply these inputs, the sinusoidal frequency as well as the mode at the very beginning of the 1 millisecond packet clock cycle. And as a guideline, we recommend encapsulating these analog primitives as well as signals of X-real and other types inside a fixture. Here is the response chain inside the same fixture submodule. We're measuring peak-to-peak amplitudes using these primitives. And since that requires a well-defined time interval, we've derived 2 timing signals tick and tock from the packet clock. They're of type bit converted to X bit. And over this yellow highlighted time interval, we make the measurement and then forward those real peak-to-peak amplitude values over the interface bus up to the monitor. Notice we've allowed a half a cycle of time for transients to settle out. To summarize, this X model flow is compatible, at least in concept, with the Accelera UVM AMS standard. The fixture plays a similar role to the AMS harness. It contains the DUT, as well as these X model primitives that act as analog resources to apply analog inputs or measure analog outputs. The only difference is that with X model, we don't need co-simulation or user-defined RNN modeling. Let's devise a basic test plan. The feature we're trying to test is to apply a sinusoidal input to the filter's analog input of random frequency and also a random mode, in this case M7. And oh yeah, we want to be sure to deassert the control bypass bit in normal mode. And so we can measure the peak-to-peak amplitude. Turns out to be 104 millivolts. Dividing that by 200, we get the measured transfer gain, the actual gain of the filter, 0.52 in this example. Let's talk about our packet class. These signals inside the fixture need to be assembled into a packet to communicate with the higher levels of the UVM hierarchy. And we reuse the same packet class both for driver side packets transmitted into the DUT as well as monitor side packets extracted from the DUT. And they contain fields for the randomized frequency and mode, peak-to-peak amplitudes, and identifying tags. So we can now generate sequences containing these constrained randomized packets. Here's our first sequence. This just runs the basic feature test for some number of times determined by a knob from the command line we call trials. And the frequency is constrained to the operating range of the filter, anywhere from 10 to 120 kilohertz. We even constrain the mode to make it a cyclic random variable, minimizing the repetition of the 8 modes. And we also compute the filter gain. Then we transition into the second sequence, put the DUT in power down mode for inactive iterations, another knob, and then we recover and we resume the basic feature test to keep it simple, just 4 iterations. So for sequences 1 and 3, the DUT is in normal operating mode, and these are the constraints, and this is the measured gain. In sequence 2, we've powered down the filter, and we spend inactive -1 cycles in this power down bypass state, and then we transition to a single wait 1 cycle where we restore bias and supply voltages. We can get some checking done even during these inactive cycles by writing a SystemVerilog assertion. This one here checks whether the bias voltage has returned to its nominal value of 700 millivolts plus or minus 50. And as we'll see in a few slides, when we look at the detailed property code, we can include a real value within SystemVerilog assertion syntax within restrictions. Here we're asserting that property using standard UVM reporting methods with severity, info, or warning to generate pass or fail messages. So to summarize, above the fixture level, we've got a standard UVM test bench, purely digital, and it's compliant, at least in concept, with the Accelera UVM AMS standard. Here's our typical sequence code. They're all similar, so we'll just look at sequence 1. The body task is an algorithmic packet generator that creates a packet, deasserts the power down bit, puts the DUT in filter state, and then for trials iterations, increments the packet tag, randomizes its RAND fields, and finishes that packet on the sequencer. The pin level timing details are not included here. They're left entirely up to the driver and monitor code. And I forgot to mention at the end of the talk, we'll cite 2 earlier papers if you're interested in some of these coding details. Can't cover too many in 24 slides. Here is our test suite class, which launches 3 sequences in consecutive order. Since this is a SystemVerilog task, all the executable code shown in blue here executes in begin-end order, so we can be sure all these 3 sequences are launched consecutively. Sequence 1 is created. We pass down the trials knob to the sequence object, and we then start the sequence on the designated sequencer, which is just a UVM base class sequencer. Then we launch sequence 2 and 3. At that point, we're ready to drop objection, allowing the phasing system to halt the simulation. But whoops, we need to allow over a half a cycle of settling time to measure that last peak-to-peak amplitude. So to avoid the simulator halting prematurely, we set a UVM drain time of 1 millisecond. Here's our top-level module. We know that in UVM, the test suite code is never instantiated directly. Instead, the top-level module invokes the run test method designating the test suite, and then that code is run starting at time 0. And here's the xmodel command compiling all the SystemVerilog to generate a ready-to-run executable in VCS. So this is the block elaborated by the VCS simulator. xmodel also supports Model Sim and Excellium, as shown in this manifest file. Here's where we bring in the UVM base classes, and here are all the SystemVerilog files listed. So let's run this. We'll launch it for 36 trials and print out the results in UVM tabular format. You can see the frequencies and modes. the transfer gain and the discrepancy between actual and expected. And even over this fairly long run, X model is accurate well within 2% of H-spice. We used the customizable do print routine to print out this data, making heavy use of the print generate method. And all that printing software is contained in an object called scorecard. Let's see how we can use an assertion to get some coverage done even in power down mode. So here we're looking at the biasing property. There is, it's triggered on entry into the weight 1 state, and it then evaluates this logical expression where VBN is the real valued bias voltage from this node, evaluated by a measure value primitive on the transition of this tick signal. And as long as the overall expression evaluates to Boolean, this is correct SVA syntax. And by the way, the clocking event is specified as a default within the fixture submodule. So assertions are a valuable way to supplement UVM test sequences. Since they're highly localized to a circuit node or branch, any violation like this deliberately injected failure of the bias property shown here, you know exactly where to look for the underlying cause. Here is a typical TLM pathway where we send packets on up to the coverage object and the scoreboard. It's all initiated by the driver calling its customized write call. And then at the scoreboard end, the FIFO get method retrieves the latest data packet. And here's our look at the scoreboard on slide 21. Here is the SPICE reference model, a set of 8 lookup tables. Each one is derived from a linear SPICE AC analysis, including over 100 data points. And using a simple awk script, we converted that data to a SystemVerilog associative array with an integer index, the random frequency in kilohertz, and a real voltage, V out. So at that point, we can compute the expected gain. By the way, the correct table is chosen by a function called select table, which looks at the current mode and stuffs the corresponding table into this local variable goldref of AA type. To avoid cluttering the scoreboard with a lot of printing software, we encapsulate all the printing inside this subclass we call scorecard. That's where this custom do print routine resides. Here is our coverage object, and we want to check the how the sequences have covered values of the mode. That's pretty easy, only 8 values. The frequency range, that's easy too, because it's divided into 6 manual bins. The tough goal is to cover the cross coverage, a total of 8 times 6 bins, 48 in all. And we want to be sure we only gather metrics during normal filtering operation in these 2 states, filter or resume. And that's where we call the built-in sample method to gather coverage from inside the driver's write method. So we eventually hit 100% coverage. The brute force method shown by these red dots takes a long time, a couple hundred at least, depending on the seed. The blue squares show a quicker method where we merge data from 2 different seeds, and we've hit 100% after 152 iterations. And so that's one way to cover these unfilled bins. It's useful if you're doing regression suites anyway. And here's the VCS-specific bash script that uses Unified Report Generator to merge the database from 2 seeds. So We've shown how this X model-based flow brings all the UVM enhancements into the AMS domain, even including assertions for analog current and voltage levels. Here are the papers we cited for reference, and we invite your questions or comments.
Yeah, thank you for the presentation. It was with a lot of details. So the questions are open, so please type your questions in the chat. So while people are typing, Charles, what's the next step? What are the further developments for your tool or for your projects? What are the next improvements you're thinking about?
We are continually adding new X model primitives. We have over 100 in the set. So for example, you could write analog assertions that are triggered by a signal crossing over. And I'm also working on a more complex UVM test bench right now. And it'll involve a low dropout voltage regulator with a lot more instrumentation in the fixture.
Thank you. If you can speak a little bit louder, or because your voice is a little bit quiet, so thanks.
Oh, okay.
Thanks.
Question coming up. Yes, X model and Model Zen are all tools from Scientific Analog. You can check the website at scianalog.com or come to our booth in the Gather Town. And yes, it does work per licensing agreements. We have agreements with universities and companies, so come and visit.
Okay, next question.
The question from Jonathan is why we used an immediate assertion. Actually, this was a concurrent assertion. We moved the clocking into a default clocking block in the fixture just to make the code more concise. And since this was meant to be more of a tutorial flavor, we didn't, cover all the possible cases, which you'd certainly want to do in the real world, of course. So try to keep it simple. Thanks, Jonathan.
Charles, can I ask a question over the phone?
Yeah, I can hear you fine.
Okay. So my quick question is, you use this environment UVM based only for the reason because of the capabilities of UVM, or also there's some performance aspect to also it? Because when you run Spice is very slow. Are we still running Spice at the DUT level, or?
Oh, very good question, Sumit. No, we're not. Once we've done the characterization, we don't need Spice or Spectre anymore. So there's a big performance improvement. So this runs really fast, just like a logic simulation, yet we're handling analog without any need for co-simulation. So it's very fast.
And the 2% accuracy is, I believe, is acceptable, correct?
Yeah, even with several hundred iterations, we were well within 2% accuracy of H-Spice.
Very nice. One last question would be, yesterday I heard in the UVM AMS presentation, they have this AMS bridge. So is your fixture doing the same thing? Like
yes, I was going to put that in the chat, but I didn't want to distract. So my picture was based on the 2021 Accelera video. And since then they've updated it. So instead of calling it the harness, they're calling it the mixed signal bridge. But same idea, it's like a wrapper containing all of the analog content.
Well, we have time for just a couple of more questions. So if you have any more questions, please enter them in the chat. Otherwise, we'll move to the next paper.
Are these presentations available like online for the attendees, like for later review?
Yes, the paper is available in the download. If you got the download from DVCon, it's one of the authored talks, and you can also check out. We'll also have it on our Scientific Analog website, along with the 2 earlier papers, which simulated the same design using OOP techniques. So yeah, all these, there's 3 papers available.
So there's one last question from Jonathan David. So if you can, is it possible to bind the harness to the dot?
Yeah, we've actually been playing around with using the bind command and thinking about, could we have several different fixtures available and bind one of them to the dot at any one time. Maybe Jonathan can help us figure that all out.
So thanks, Charles. Very good presentation. Thank you for your time. Very interesting. Thank you.
You're welcome.
Move to the next one. So Steve from Samsung, are you here?
Yes, I'm here. Can you hear me?
Yes, we can hear you good. Thank you for joining. So I'll do a quick biography and then we'll start playing the video. And then for the presentation, then we'll go through questions again. So yeah. So SangGi Steve Doof from Samsung Electronics is an experienced library design and verification engineer. He has a lot of history in working in the consumer electronics industry. He's a strong engineering professional with a master's from UNIST, South Korea, and he has field experience of design enablement team at Samsung. Currently, he's working for advanced technologies in the embedded memory modeling group, and he has related verification views, including MBIST and Samsung at Samsung Foundry. So thank you for being here and thank you for submitting your paper. And yeah, we're going to start playing the video. Please go ahead, play the video. Thank you.
Hello, everyone. Thanks to joining my presentation. My name is SangGi Do. I'm currently working for library engineer at Design Enablement Team Samsung Foundry. Today, I'll present my 2022 DVCon U.S. paper titled Mixed Signal Functional Verification Methodology for Embedded Non-Volatile Memory Using USB Simulation. This work is co-operated by my colleagues, Ms. Jieun Park, Mr. Dohui Kim, and Mr. Jungkyu Jang. I would like to take this opportunity to thank my colleague. This is index of today's presentation. First, I'll briefly explain what is functional verification, why it's important, and what is difficult point. Next, I'll introduce what is ESP simulation. Third item is comparison between ESP simulation and our proposed verification methodology. And then I'll introduce some detailed steps of our verification methodology with example cases of module conversion technique. Last, I'll summarize our experimental result and conclude our works. Functional verification is essential step of IP validation because it verifies the operation of IP in terms of functional operation. From the perspective of SoC design, even a single small component has significant impact on the overall chip design if a functional operation has some kind of problem. Therefore, the importance of functional verification is more prominent in the foundry business. For digital IPs, several commercial tools support functional verification such as synopsis formality or cadence conformer. However, there is no golden solution for analog circuit verification or mixed signal IPs without SPICE simulation. Of course, SPICE can provide functional verification result of IPs. However, runtime of SPICE simulation increase exponentially following the design size. Especially large size mixed signal design IPs such as memory design are unable to run SPICE simulation due to the runtime issue. So to overcome this runtime limitation, Synopsys provide mixed signal functional verification tool by their own verification EDA tool, which called ESP. ESP support functional verification for limited number of mixed signal IPs, such as SRAM, ROM, and CAM. This tool is the only EDA tool which can support direct functional comparison between SPICE NetList and Verilog behavior model without using SPICE simulation. Therefore, Samsung Foundry has been using ESP verification flow for solid and reliable verification tool since 2017. By using their own data type symbol, ESP compared the static and dynamic simulation result. But however, not only the limitation of supporting IPs, ESP support only synchronous design, but it supports multi-cycle operation. So we cannot use various asynchronous design for ESP simulation. So due to the limitation of ESP supporting IPs, we proposed our verification methodology for non-supporting IPs by ESP tool. So using Verilog versus Verilog comparison function of ESP and extracted Verilog model from NetList, we successfully compared the NetList and Verilog behavior model by using our proposed methodology. However, to enable the extracted NetList for Verilog simulation, we have to modify the extracted NetList. Also, for simulation runside, we need a custom test bench for our proposed methodology because ESP does not support extracted NetList natively. Luckily, using Verilog language, we can create custom test bench for ESP simulation. For extracting base NetList from designed schematics, we use Cadence Virtuoso NetList extraction feature. However, we cannot use base extracted NetList for Verilog simulation directly because extracted NetList does not support analog delay characteristics, and there are some unsupported devices in there. Also, extracted base NetList can have some kind of signal collisions or infinite loop problems. So to resolve this problem, we modify base NetList, base extracted NetList using various modeling techniques. From this slide, I'll introduce some model conversion techniques. So this example is transistor replacement. Some case of model conversion could be simple as this example. This schematic is a level shifter, and due to the conflict signals, it does not work properly. So let's look some detail operation. When voltage level of in rise, N2 is closed and N1 is opened. So that cause A1 short with ground. However, A1 is conflicted with logic high, which comes through P1 when out signal is low. As a result, in digital perspective, A1 goes unknown value. According to unknown value at A1, out goes unknown value. However, by replacing the MOS transistor with RMOS, transistor distinguish the signal priority and solve the conflict problems. Because RMOS gives signal priority rather than MOS transistor. So let's look some detail operation when we replace the MOS to RMOS. When in is set to high, N1 is opened and N2 is closed. Depending on the N1 and N2 setting, A1 connects with ground. Meanwhile, A1 is determined as ground because in this case, priority of logic high from RPMOS P1 is lower than ground, which is coming through N1. According to fixed A1 ground, RPMOS P2 is opened and out goes high, and RPMOS P1 is closed. Because when in is set to low, N1 is closed and N2 is opened. Depending on the N1 and N2 setting, out, which has high value, transferred to the ground value through N2. Because the priority of ground through N2 is higher than logic high from RPMOS P2. According to out value transition, RPMOS P1 is opened and A1 goes logic high and RPMOS P2 is closed. That's how the RMOS solve the conflict problem of this kind of schematics. Second example is loop cutting. So feedback loop is common scheme for circuit design. We commonly use this kind of infinite loop. In analog simulation, feedback loop stabilizes the value of a node to maintain a certain value voltage level. However, in case of digital simulation, feedback loop can crash the net value due to the signal confliction or fluctuation the net value due to the periodic signal assignment. Therefore, feedback loop should be removed from circuit during module conversion. So let's look some detail operation. When clock is high, V out is set to V in. When clock is low, V out is maintained. However, when we run the digital simulation using schematic, node A goes unknown state and V out goes unknown. To solve this situation, we create behavior model for latch. Latch behavior model assign V in to V out when clock is high and clock bar is low. If clock bar is not low when clock is high, we assign unknown value to V out. For this case, we simply replace the net schematic to behavior model. If your design uses standard cell design, you can also use Verilog model from standard cell library. Last example is bit-cell modeling. MRAM determines bit-cell data 0 or 1 by using magnetic resistance effect from magnetic tunnel junction, which called MTJ. Sense amplifier determines the data value by comparing the voltage level of source line and bit line. Therefore, this schematic does not support digital simulation at all. Also, MTJ device does not support digital simulation. Therefore, read path, including bit-cell, must be modeled for digital verification or digital simulation. As you can see from the figure, blue box is modeled part and it creates reference and input voltage to sense amplifier, and that enables the proper bit-cell operation. So let's look at our experimental results. This is a coverage analysis report from our ESP simulation. This coverage report is generated by ESP tool when the symbolic simulation is completed. From the table, IMP represent implementation design, which is extracted netlist, and REF means reference design, which is behavior Verilog model. Symbolic net indicates the net which is covered with the symbol value at least one time during the ESP simulation. Line coverage is a simulation touched line from reference or behavior model during ESP simulation. As shown in table, symbolic net coverage of implementation model is higher than behavior model for all IPs. This is because implementation model from circuit uses bi-directional port, and it makes easier to propagate symbol value through the netlist back and forth. Besides, behavior model mostly use directional port, and it restricts the symbol value to propagate from input to output only. Symbolic net coverage cannot be 100% due to the functional characteristic of IP. However, from the result of line coverage, we can check that ESP symbolic simulation tests more than 99% of entire model for all IPs, and it guarantees the reliability of verification simulation. For other side of ESP simulation, computing power is also important. It's hard to find the reference ESP simulation computing power, but luckily we could find ARM's ESP simulation computing power from SNOG 2021 presentation. So upper table is computing power of our simulation, and below one is ARM's result. We tested 3 different types of IP, and the size of each IP is different. In case of ARM, 2 different size of EMRAM are tested. It is difficult to compare the result between our simulation and ARM's simulation result directly, because we do not have detailed simulation results related to different cases of ARM, such as coverage report and symbolic simulation setting. But however, when we compare the average computing power from known simulation data, considering memory requirement at runtime and memory size, our simulation is much efficient than the simulation result of ARM. This kind of runtime efficiency is very good advantage to decrease TAT of IP validation. So as conclude our presentation, despite of hardness of mixed signal functional verification, our ESP simulation enables functional verification of mixed signal IPs without using splice simulation. To improve the reliability of fundamental IPs of Samsung Foundry, we have proposed a mixed signal functional verification methodology for non-volatile memory using list extraction and ESP symbolic simulation. Our proposed methodology successfully enabled mixed signal system level functional verification in short time with reasonable computing power. Since 2020, Samsung Foundry applied this verification methodology for all supporting ENVMs such as eFlash, EMRAM, and OTP, including advanced technology nodes such as 5 nanometer or 4 nanometer. In addition, our proposed method can expand to various types of mixed signal IPs. Furthermore, our generated simulation model using list extraction technique supports various Verilog simulator such as Cadence, Excellium, Synopsys VCS, or Mentor Questa. So that's it. Thank you for attending my presentation. If you have any question about our works, please contact me by email. Thank you again.
Thank you, Steve, for the presentation. So reminder, please type your questions in the chat, and a reminder, please do not forget to vote for the best paper. We have really good papers in this presentation. So a question, so while people are typing the questions, I'll ask a simple one. Steve, you said the symbolic net coverage cannot be 100% due to limitations of the characteristics of the functional IPs. Can you tell us more about these? What are these limitations?
Actually, we cannot set all symbol type for all input because for some specific reasons, there must be some pins should be tied for certain value. That's why we cannot apply symbol to such some number of pins, and that caused the degradation of symbolic coverage.
Thank you. You have two more questions coming that they're piling up. So if you want to go through
okay.
one.
The first question from Joachim. Yes, in case of our verification, we just assign some supply for power and ground pins. So we don't consider such a power simulation. The second question is, so the RPMOS and RMOS is, they have some, they can distinguish the signal strengths and behavior a little bit different with normal NMOS and RPMOS. So in case of our using case, it solved the X conflict, signal conflict, it solved the signal confliction. So that's why we replaced NMOS, PMOS for RMOS and RPMOS.
Questions from Surab.
Yes. Actually, I don't understand what is synopsis netlister. Maybe it's some kind similar with some Betasoft netlist extraction. So maybe, could you elaborate more your question? So
have you used the synopsis netlister or not?
We don't use that.
Okay, so you can move to the next question. Though, thank you, Johan, Jonathan, for the RMOS, RPMOS.
Oh, thank you.
Yeah.
Thank you.
The next one is Bill Moore.
Yes, that's a weak point. So currently module conversion is some modules are purely manual and some modules are automatically generated by our own process. So it's quite hard process to make module conversion, because if we do some manual process, it takes a lot of effort by designers. So, and then and this, your concern is right, that equivalence between source and converted module quite be risky, but as we saw the entire netlist, our manual processing portion is quite little, and usually it's a base component. So we agree that it does not impact much.
Any other question?
So adding some more information, currently our main focus is verifying the functional operation of our embedded memory. So we just simplify the analog part from our IPs and run the digital verification simulations. But as we if we can expand some more works for analog part, maybe we can adopt some other tools or other techniques such as X model, then we can run the entire verification simulation much solid. We can get some solid result. So that could resolve some concern from Bill.
There are two other questions, one from Jerry and one from Jonathan.
We did not sense the, we don't have to sense the such a kind of structure like level shifter or current mirror, because we build our own IPs, so we know which part is level shifter or current mirror. So we don't sense, but we can we just know by the name, module name. So last question from Jonathan. I did not try that, but maybe it could work. So I have to try it.
We have no more questions. We're going to switch to the next presentation. So thank you, Steve. It was a really enlightening presentation. Thank you for your efforts. Thank you very much.
Thank you. Thank you all. Thank you for all the questions.
And Steve has put his email right in the slides. So, and the proceedings are available to everybody.
If anyone has further question, contact me by mail, or you can leave some question from the virtual platform.
Thank you, Steve. Thank you.
Thank you.
We'll move to the last part. So again, please do not forget to vote for the best paper. It's important. And the last presentation will be done by Rock Shi, and he's working at ADI Analog Devices. He's a mixed signal design verification lead. He has interest in the design, modeling, and verification of analog and mixed signal ICs. He has a PhD from the University of Maryland at College Park. And before he joined Analog Devices, he worked at Infineon Technologies as a mixed signal integration, and also at Agilent Technologies as an analog designer. So yeah, we can go ahead and play the presentation. Thank you, Tasmia.
Hello, everyone. Thank you for joining me with my presentation. It's my pleasure to present a paper with 4 co-authors: Padmashree, Chaitanya, Kunal from ADI India, and Preston from Boston, United States. The AMS methodology perhaps exists from the very beginning of mixed signal IC design practice. In general, AMS flow run with either behavior model, say Verilog A, or SPICE primitives. It's become less favored in modern IC verification flow because of its speed slowness due to the SPICE simulator. And its role has become less clear since the emerging dominance of the so-called digital mixed signal DMS methodology. So in this paper, we try to reevaluate the AMS role and try to analyze AMS versus DMS, when and why both are necessary and can be complementary. How we can take advantage of each flow's strengths to optimize verification resources and job efficiency. MSDV is becoming an emerging industry discipline and dedicate new career paths. So it's the interest of this paper also try to identify its role, function, and also to present some common activities. So the first thing we want to point out is the key to the success of MSDV is the annual behavior models. In fact, the availability and the quality, the term quality will be defined later on, of models for analog circuits have a large impact on the flow to use and the quality of the verification as a whole. DMS modeling has been found its limitation in capacity and efficiency when modeling some type of analog circuits. The real number modeling, either SystemVerilog real net tab or Verilog AMS W is in essence a digital modeling approach. Basically, they're digital models, right? So analog designers are not necessarily familiar with, and they may not necessarily be willing to learn and use them. For them, these digital models always require running digital simulator in addition to SPICE engine, right? So analog designers continue to prefer using AMS models in their design phase for some good reasons. That is, the DMS models that are preferred or desired for the full chip verification are usually not available from the design team. It's up to MS-DV team or DV team to develop these models. And that also means the DMS models developed is solely for the verification purpose. Rarely we find it will be or has been used by the analog design team. In fact, this is really a gap in the current industry practice. So in our paper, we are using a PL test case to show and illustrate the modeling style approach, pros and cons between the AMS and the DMS models. So we also put the emphasis on two building blocks to illustrate, in the paper, specific models, AMS models and the DMS model for these two building blocks. On this left box is the charge pump. On the right side, this box is a loop filter, right? So join here this net between the CP out, the charge pump out, to the LF in, the loop filter in. This particular net is also a special attention in the paper and also the presenting here. So because of the three capacitor here, basically we will have to solve the third order Laplacian or Z-domain transfer functions. So let us first try to identify some challenges of a real number modeling. Without SPICE engine in DMS flow, by the way, that's the advantage of the DMS flow, because we don't have SPICE, so we don't have the speed issue. Then DMS modeler himself, the human being, is the analog solver. He or she has to perform load or loop analysis and has to solve the differential equations in a digital way. And the signals in real number models by default are voltages for nets or ports, right? That means a real value in DMS models, even though we can interpret it as a current, but we cannot have both. We cannot have both voltage and currents. This probably is not a problem in most of the applications, but it does introduce some difficulties in modeling, say, in the situation where both voltage and the currents are in the play on the same net. Of course, advanced SystemVerilog features is available, right? So like a user-defined type, it enables us to model a net to carry both voltage and the current simultaneous. Next, the E net, all right? So we have both voltage, current, even impedance. And also we have the user-defined resolutions, like the summation resolution, for example. It can be used very well for modeling the current summation for the Kirchhoff's current law. But using advanced feature like this definitely introduce some extra effort, because DMS model itself is not easy by itself, right? So we have to handle all this special data type and in the whole environment. For example, it makes the AMS simulation more complicated when, say, we put the model together with the electrical, like a schematic. You have to handle the special interface between the digital and the schematic. DMS model definitely has some impact on circuit partition and structure. Say we prefer everything put in the box. We don't like the individual or discrete element like a resistor or a capacitor outside of a box, right? So the quality of analog behavior models, we have talked about that. So let's talk about the quality of the analog behavior model, because we want to compare the AMS models and the DMS models. So in the paper, we define the quality of analog behavior models in this context. First, we want to say the model will be used for full chip verification, because we're not talking about a model for, say, design phase, like top-down design. It is mainly for the full chip verification. So at the minimum, the model should facilitate the full chip AD analog digital interface connectivity check and the major functionality check, right? And ideally, the model should also facilitate some very detailed special analog behavior or some analog performance metrics. And the model should be validated and keep updated whenever there is analog design change. By the way, this will not be easy because analog design keeps changing. You have to keep updating, keep validate the model, right? So this is the challenging of the process. So given the definition of the quality in this context, we claim that developing high quality of DMS models can be time consuming. Say, if you want to have high quality DMS models, that often means that you have the modeling down to the lower level of hierarchical structure, right? But if you're doing so this way, then the whole modeling development validation process will take a long time, because low level analog design keeps changing. They may keep changing even before ready for the tape out. So, and also DMS model doing this way become nice reusable. Because someone would argue that, hey, you are talking about DMS model takes time. How about we develop one time and then next time, next project, we will reuse that. But as we claim here, we are doing the low level modeling to get the higher quality of the model. Then it becomes so chip specific. And then next time you have a new project and your previous models probably is not that useful because they are so chip specific, right? So our conclusion here is the time a DMS model saves in a simulator can be traded off by the time to produce that. On the other side, the AMS models, right, although they're slow in simulation, they can be produced much faster with very nice, much less validation effort. So in the paper, we have a very specific comparison for both the loop filter and the charge pump. But in the presentation here, we're showing we're only showing the loop filter. This is actually this is the AMS model for the loop filter. So in at ADI, we have develop a library of behavior models for all the primitives, stem cell, and so on. Analog designers just drop in the schematic symbol, right, into the schematic, and that's it. That's the model itself. So this way, we would say the AMS model can be developed very fast, and it's like the schematic, as you can see here. So on the other side, DMS model in the SystemVerilog example here. So we want to first, this is the third order transfer function, Laplacian. We need one way, by the way, is to use the bilinear transform to convert this Laplacian function to a Z-domain function, right? So we can just realize this G-1 simply just a unit delay. So we can relatively easily to implement a model of this function. By the way, all these coefficients, right? They are related to all these R and C's in your loop filter. Whenever you have RC change, you will have to update these coefficients. You will have to remodel and revalidate again, right? So that takes time. So showing here is one snapshot compared with the AMS on the left here and the DMS model on the right side, right? So the red trace is loop filter output or the VCO tuning voltages. Looks pretty much similar between the two models. So at the bottom trace, like this bottom trace is the time for the PL to get locked. So compare with the AMS and the DMS, it's about the similar time. So in general, we can say, yes, the DMS models does have the capability to achieve the same quality as AMS models. It just takes time. And showing this plot is an example. Try to explain. We do have a case when both voltage and currents are needed for the DMS model. So in the test, we have the specially doing special disable the oscillator input, the crystal. And then the phase detector will only have the down signal. That means we'll keep discharging. So the loop filter voltage discharging down. And then when they discharge down to some voltage, say 100 millivolts, right? Then your charging current, discharging current is no longer constant. It's dependent on the voltage itself, right? So this is the case why both voltage and currents we really has been modeled in the in some particular case. So we are trying to in this presentation we try to illustrate how we could accomplish our IMS-DV task by using a hybrid of AMS and DMS models. As I probably explained already, AMS model in our case are from the analog design team. They use them in their design phase. So we claim they are 100% model here. And we have models for the DMS, which is a 100% model. Say PLL, all these relatively easy and common used blocks because they will be used for all the tests, no matter it's digital test or the AMS. So we actually model them carefully. We claim they are 100% model compared with AMS. We have some block just 80%, some just 6%, and like this block we only have 20%. So the reason is that because this is a separate tape out, is actually reuse IP. We don't need too much digital verification, so we can just count on the 90% actually verification task actually from the AMS models with the AMS flow, right? So this is how we can use a hybrid use AMS and the DMS model together to finish all the testing requirement. So we have identified three categories, right? So in our practice, so the first one is we better just use DMS because they're more relevant or more efficient. And the second category is we use a combination of AMS and DMS because it depends on if the model is available or how good is the model. And then there is a category definitely always is you have to use AMS. So for example, we always do the full chip transistor level sanity test check. Then say for example, we want to make sure the power sequence, power up sequence is always working. So that's a classical AMS because we really need to run the transistor level simulation. And say in the case of use the DMS, say we want to turn on the test bench, right? at the initial stage of the project. And that's how we better to use the DMS. At that time point, the schematic, the AMS model probably is not that clean yet. And you don't want to get in trouble of this convergence with the electrical stuff. And the AMS is not very efficient. And say for the gate level simulation, DFTs, AMS, we do run AMS with these two category. But in general, this has been done mostly in DMS or digital test. We use AMS as a kind of a double check only, right? So these are kind of things we find better to count down both AMS and the DMS. So for example, when we count down, we at the end of the project, we want to see how well we cover the whole register map. You will always find some DMS test or digital test. It's hard to cover some pins because the model do not model that pin at all, right? So you may have to go to the AMS flow to cover that register. So this is the three flow choice decision and tell us when AMS is better and when DMS is better. So running AMS and the DMS, running two flows doesn't mean we have to maintain, we have to develop two test bench, right? So in the UVM nowadays, we actually have a good chance to unify these two flows under one infrastructure. And this is a high level abstract view of how we do, how we run two flows in one infrastructure. The TP harness is a shared UVM test bench, right? So the green, which is a DMS flow for the DMS nannies. And this orange is for the AMS nannies, AMS flow. So in our practice, we only need a compiler switch to switch from the DMS flow to the AMS flow. So in general, we will say sharing the same test bench with the digital flow is a huge advantage to the AMS, because we no longer need to worry about how we could drive a register, how could we load the memory. Of course, because you are running together with the digital stuff, each time you run the AMS now, you actually have to spend a little bit more time, but that's fine. Okay, so MSDV, we want to say is now becoming a special, like the discipline, design verification as a discipline or design verification engineer as a career path has been in the industry for probably decades, right? So, but only until recent years that MSDV has been identified as a separate discipline, or MSDV engineer as a new career path. So individual practice in MSDV varies across different companies or even different business unit in the same company. But still, we can outline some common activities of MSDV team. So first thing, we need to involve and responsible for full chip verification test bench creation. It takes time at the beginning because now you probably have to make sure your AMS flow is compatible with the DMS flow. You have two flows, then how do you make two flows working together? Yeah, this is the initial stage of the project. And then we need to spend time to develop models for analog circuits, either DMS models or AMS models. In our case, AMS models come from analog design team, right? But it's still, we need to integrate them to the in the UVM and the test bench, right? So we still need to spend some time. So I would say modeling, development, and validation takes time. Then we need to create nannies, either DMS, AMS or both. And then this MS-DV team need also maintain the netlist, right? The netlist release. That means you also need to keep the models updated together with the netlist release. And then we spend a lot of time at the end of the project to develop a MS-DV test. These are a subgroup of tests that focus on the analog blocks, the interface between the digital and analog, to make sure some analog behaviors, right? Even some analog performance metrics has been covered, verified in our test suite. Okay, so conclusions. Our first conclusion is that the popular industry adoption of DMS flow for the full chip verification does not necessarily mean that it is a full replacement of the AMS flow. So, unlike the early stage in the mixed signal practice, AMS was the only dominant flow by that time. And now DMS flow is unlikely to become the sole flow, the only flow in MS-DV. Perhaps both AMS and DMS will coexist for quite some time, right? And also we point out that there's a trade-off between the DMS models. They can save in simulation time and the time for the models to be developed. And also we point out that the MS-DV is becoming an emerging separate discipline, and also MS-DV engineer is becoming a new career path. Okay, my time is over. So this is a big thanks to our colleagues. And now let's go to the questions and answer session. Thank you all again.
Thank you very much, Rock. Very good presentation. Thanks. So you already have a question from Jonathan David. You can read it and let us know what you think.
Rock, you're on mute.
Yes, can you?
Oh, I'm sorry. Sorry about.
Can you unmute, please? Yeah.
Yeah, I'm so sorry. Yeah. That happens. Yeah. Yeah, Jonathan. Your first question is about the pseudo electrical UDN. I agree with you. Using this sense nowadays for us, we are doing the big signal design verification as a career. It should be something we definitely should be using and try to leverage its good stuff, right? But the topic of the paper, I have something in consider with the analog design team. The topic is the model we use, even for just the straightforward DMS models, is already not that easy to be used by or adopted by the analog designers, right? And if we're using this UDN or even ENet, and it will be even harder. And if you use that model to drive the schematic and the interface, the connect modules, all the things are become more like, of course, there's a learning curve here. I agree, yeah. So that's my point. So your second point, you said you are a pioneer of MS-DV. You identified this as your career path in 2005. Yeah, that's great. My observation is, many of us already have been doing this mixed signal design verification even 1 decade ago. But at least in my case, I was an analog designer, for example. When I'm doing that kind of job, I didn't realize this is actually can be separated a career path. And the company didn't actually identify you as or identify your activities. Say you are doing MS-DV for this part of the work, right? So even so, the point of the paper is only recently, at least in my company ADI, we officially have some job titles. Say I myself now is MS-DV engineer, right? So this is kind of officially identified by the industry now. Okay, we definitely need have this dedicated career path for some people like you, even though you started very early, and I think you probably are really a pioneer in this career path, which is good. Let me see other questions. X models. I noticed X models. I read papers. I think Nime is here. Nime is my really a mentor in my company. I myself didn't evaluate the X model. I think that's a very interesting and promising. But maybe Nime, you have any insight for X model?
Yeah, I just responded to Jonathan.
Oh, you responded. Okay. We evaluated X model a couple years ago and did see a few benefits, but there are outweighed by actual work. Okay. I myself, this is my personal biased feeling, right? So we recently run a memory with Spectre XPS, and we feel because the results are completely different. And XPS is basically the lookup table models, right? Simplified models. And my concern for the counting on all the X model things, basically we are assuming we can use the SystemVerilog model languages to do some simplified model or equivalent model as we did in SPICE. I bet there is some limitation there, but I would like to try that. But I think there is some nice part of that. But I don't believe you are completely replaced by just using machine-like model like that. Basically, we're saying all the transistors, we no longer need a BC model by the SPICE language, right? Or we will just use the SystemVerilog language. I seem to say there is some challenge here, but I didn't try that, so I cannot answer this question very well.
So we have Nimesha has answered few things to Jonathan. So there's another question on DMS models. If you prefer SV real number modeling real type or Verilog AMSW reals?
Oh, okay. Yeah, I can answer this very well. We started to use the Verilog AMSW before SystemVerilog real type. So by that time, that's the only thing we have, right? So this is a big topic in general. But of course, because of the user-defined data type, all the things by SystemVerilog, and the SystemVerilog has some advantages to model. Say you have to model both current and voltage. But real cannot do that, right? Because they don't have that in the 20 years ago. So on the other side, because the SystemVerilog AMS is stuck there, right? We don't have SystemVerilog AMS language. We did that, but there's no plan to get that out, right? So Verilog AMS will still be a very important language. In fact, this week we are going to discuss that. Should we actually enhance the Verilog AMS, or should we actually continue to try to get out of the door for the SystemVerilog AMS, right? So Verilog AMS W, because it's AMS languages, even though to model the digital languages like the model I'm talking about in the paper, I don't think that they have all the capability in the SystemVerilog real net type. But if we are using Verilog AMS, we are more easily to handle all the other things with A part. So this is a big topic. It's hard to explain here. I do have very good insight in the subtleties here, but the only unfortunate thing is the SystemVerilog AMS is not produced yet, and we probably won't be able to see that for 1 or 2 years, right? So in that case, if we want to really resolve all the AMS challenges or problems or modeling issues, I think Verilog AMS still very good things to keep and keep use.
The time is over, but we'll go for one other question, 1 or 2 other questions. So Sanjay Chatterjee from Allegro. So you can see the question: how are the analog design changes propagated into DMS and AMS models? Do you maintain a model specs as your golden reference?
I didn't understand the propagated changes propagated. How are analog design changes propagated into DMS models? Do you maintain models? Yeah. So honestly, I don't understand the question very well. I'm assuming is that asking for any changes? How do we update the model?
I mean, Sanjay, can you unmute and clarify? Thanks.
Yeah, sure. so when we build up a model, DMS model initially, we build it based on some model spec, definition of the analog model, functional definition. But then the design might change, the analog design might change. So how is that synced up with the DMS models?
Yeah. This is a great question. This is in fact is why I claim the DMS modeling is time consuming. Really, the whole process to tracking the changes and then re-update and revalidate the model keeps time, right? In ADI, I myself just run the AD or kind of AMS test plan, make sure any change, the model still be updated. We do have UVM-based model validation flow. My observation is not very many people actually use that because there is no time to do that. But on the other side, you can think about AMS models. You change the capacitor and the resistor there, it just a change the schematic and the model is there already. You don't need to validate again. So that's the whole point. The DMS keep the DMS model following the change of analog. That's not easy. It's really not easy. Of course, if we have everything can be done by X model, then we don't worry about it because X model down to the device level, right? So that's a very good thing. But again, I have concern if every circuit I will be handled by the X model. I don't have the confidence like that. Yeah, but this is a good question. Yeah.
I think that's it for the question. Is there anybody else for one last question, or otherwise we'll just wrap up and close? Yeah, it was a very, very nice discussion, good discussions in the chat and good answers from Rock. So I think there's no more questions. So again, please vote for the best paper. And yeah, thanks everybody. Thanks for this. Thanks for attending and enjoy the rest of the day with DVCon. You can visit the vendors and you can, yeah, good luck. Have a good day. Bye. Thank you.
Yeah, thank you. Bye.